So a very good morning to all of you. In this part, we will cover gas cycle refrigeration, and in this gas cycle refrigeration, we will solve a numerical on the Bell-Coleman cycle, which is also known as Joule cycle or reverse Brayton cycle. So here the question is, the air refrigeration used for food storage provides 25 TR. TR stands for tonnage of refrigeration. The temperature of the air entering the compressor is 7 degrees Celsius. Temperature at the exit of cooler is 27 degree. COP of the cycle, we have to find out the COP. So first we will write what is given to us. So in this question, it is given to us that the refrigeration capacity is 25 TR, tonnage of refrigeration, and the temperature of the air entering the compressor is 7 degree, which is equal to 280 Kelvin, and temperature at the exit of cooler, that is 27 degree or 300 Kelvin. We have to find out now. We have to find out the number one, COP of the cycle. Number second, power per tonnage of refrigeration. Power per tonnage of refrigeration required by the compressor. The mass flow rate of the air which is circulated in the system is given. Mass flow rate of the air is 3000 kg per hour. So we can convert this thing into like kg per minute and kg per second. Then the compression and expansion both follows the law PV raised to power 1.3. This is very much important here because it is not following the PV raised to power gamma curve. Then take the ratio of specific heats gamma, which is 1.4, and this specific heat at constant pressure is 1 kilojoule per kg Kelvin. So these are the input parameters. Now we'll start our, first of all, we'll draw this TS diagram. Yes. So we will draw first the ideal cycle, ideal TS diagram. One, two, three, four. Where 1 is the entry to the compressor, 2 is the exit of compressor, 3 is the inlet of the expander, and 4 is the exit of the expander or the entry to the refrigerator. Now, in this question, it is clearly mentioned the compression and expansion both follows the relation with PV raised to power 1.3 equal to constant. So now the TS diagram, how does this TS diagram will look like if the compression process and the expansion process follows this law. So what we are going to do, this is the pressure P1 and this is the pressure P2. These are the constant pressure lines on the TS diagram which are of the diverging nature. Now the PV raised to power 1.3, what does it mean actually? Just a second. Yes. So in this thing, the compression will follow this curve because this is the process 1 to 2 dash. 1 to 2 dash is basically polytropic compression with cooling. Polytropic compression with cooling. Polytropic compression with cooling. Actually, the concept behind this is like if the curve will be on right side of this isentropic process, then that would be termed as polytropic compression with friction. Now, in this part of 1 to 2 dash, the cooling is simultaneously happening in this process. So this is not an adiabatic process. Rather, 1 to 2 dash is reversible process with cooling. Reversible process with or reversible compression with cooling. So this happens in the compressor, and what we do for this cooling part, we provide water jackets outside the body of the compressor. So this process can be achieved 1 to 2 dash, and then the process of that expansion in the expander that will be not reversible adiabatic compression, rather it would be 3 to 4 dash polytropic expansion in the expander. So we have to, here in this, we have to first find out the T2 temperature and then T4. So now in this question, very important part is pressures are not given. So how will we proceed? Firstly, we will take this thing as refrigeration capacity. Refrigeration. So first of all, we will see the refrigeration capacity. Refrigeration capacity in this problem is given as 25 TR, 25 tonnage of refrigeration. And we all know that 1 tonnage of refrigeration is equal to 3.5 kilowatt. So this comes out to be 87.5 kilowatt. Refrigeration capacity of this system, which is based on the Bell-Coleman cycle, is 87.5. Actually, why we have to do this? Because in this question, the P1 and P2 are not mentioned. So if we do want to calculate this T2 for finding out the COP and this T4 for finding out the COP, we have to find out this T2, and the pressure ratios are not given. So what we are doing, we are just writing down this relation of refrigeration capacity in the cycle, refrigeration capacity in the cycle, ये प्रोसेस हो रही है 1 to 4 or 4 to 1. So in the process of 4 to 1, this refrigeration capacity can be written as mass flow rate of air into Cp of air into T1 minus T4. So refrigeration capacity is given as like 87.5 kilowatt, and this mass flow rate of air, it is given as 3000 kg per hour. So what we will do, this will convert in kilogram per second. So 3000 divided by 3600 into Cp, that is mentioned as 1, and T1, this T1 is given to us as 280 Kelvin minus T4. So on solving this thing, this T4 comes out to be 175 Kelvin. 175 Kelvin. Now this T4 is available to us. Now we will see this thing as T2. We will find out this T2, and we know that in the process of 1 to 2, this T2 by T1 is equal to P2 by P1 raised to power gamma minus 1 by gamma in the process of 1 to 2. And likewise, in the process of 3 to 4, we can write this T3 by T4 is equal to P3 by P4 raised to power gamma minus 1 by gamma. And the process of compression and expansion are following the law PV raised to power 1.3 equal to constant. So in place of gamma, this will be replaced with N. Gamma will be replaced with N. So we can write in from these two relations that T2 by T1 is equal to T3 by T4. We have calculated this T4. We do have this T3. We do have this T1. So by this, we can find out the value of temperature after compression. And on solving this, the temperature of compression after compression comes out to be 480 Kelvin. 480 Kelvin. Now, for the COP, now all the four temperatures are available to us. Now for finding out this COP, we all know this can be written as T1 minus T4 upon gamma minus 1 by gamma into N upon N minus 1 into work of compression minus work of the expander. And for the work of compression in the process of 1 to 2, it can be written as T2 minus T1 minus the work of the expander T3 minus T4. We have all the temperatures with us. Gamma is given as ratio of specific heats as 1.4. N is given to us. N is available with us, that is 1.3. So on solving this, the COP comes out to be 1.13. The COP of the system comes out to be 1.13. And the third thing, power per ton of refrigeration. So for finding out the power per ton of refrigeration, number third, for finding out the power per ton of refrigeration, for finding out this power per ton of refrigeration, we will use a relation. Like we all know, COP is equal to refrigeration capacity in the refrigerator upon the power output. Refrigeration capacity, we can easily write it as m dot A into Cp of air into T1 minus T4 upon this power. So we have to find out this power. Then power will be equal to mass flow rate of air, that is 3000 upon 3600. That will be the mass flow rate of the air in kg per second. And Cp of air is given as 1 kilojoule per kg Kelvin. T1 is available to us, that is T1 is 280 Kelvin, and we have calculated T4 as 175. T1 is 280 minus 175, and upon the COP. We have just calculated the COP and it comes out to be 1.13. So power in kilowatt comes out to be as 77.12. On solving this, it comes out to be 77.12 kilowatt. So in this question, the power comes out to be 77.12 kilowatt, and we have to find out the power per ton of refrigeration. This question is designed for 25 tonnage of refrigeration, and the work output or the power which is to be consumed comes out for the 25 tonnage of refrigeration. Now we have to find out the power per tonnage of refrigeration. So what we will do, we will just divide the refrigeration capacity 77.12 or the power with this complete capacity, that is 25 TR. It comes out to be 77.12 kilowatt divided by 25 TR. It comes out to be 3.1 kilowatt per tonnage of refrigeration. So power per ton of refrigeration comes out to be 3.1. So this is the complete answer of this problem, which is based on the Bell-Coleman cycle. We have find out this unknown temperature T4. We have find out this temperature T2, COP of the system, and this is the relation which is used in case of the polytropic compression and expansion process, when both are happening with index of like polytropic index with N of value. Here the polytropic index was 1.3. So this diagram is valid whenever the polytropic index N is lesser than this gamma. So the polytropic compression with cooling will follow this curve 1 to 2 dash. So we have not calculated this 2 dash because we have used this relation of COP, where index of polytropic compression and expansion is used as 1.3. So COP comes out to be 1.13, and power per ton of refrigeration comes out to be 3.1 kilowatt per ton of refrigeration. So this was the complete problem. These are the references. Disclaimer. Thank you, everyone.